Hey Phys 1 kids, Campbell here. In our second video on forces, we're going to talk about what a force does, how to put forces together to find a net force, and Newton's first law. So what forces do is they cause changes in motion. Believe it or not, the natural state of an object is uniform motion. So like at rest, which maybe isn't hard to believe, but also constant velocity, which really is hard to believe. When there is a net force, it causes a deviation from uniform motion, which means that it actually causes an object to accelerate. In fact, let's take a look at a force example by watching these cars. Newton's first law says that an object remains at rest or moves at constant velocity unless acted on by a net force. Here my car is at rest, so let's apply a force to it. But once I'm done applying that force, it'll move at constant velocity until maybe it needs another force. Here we go. Let's give it a force. Constant velocity. Oh, force. Constant velocity. Oh, force. Now, anytime there are multiple forces acting, we need to find the net force by doing a vector sum. Now, remember that we have to take into account magnitude and direction when we add vectors. And so if vectors are at angles, we need to break them into components so that all our vectors are on the same axes. So that means if I have a vector that is at an angle, and I have another vector that maybe is vertical or horizontal, I'm going to have to break this vector into x and y components before I can add them together, just like we did in 2D motion. We broke stuff into x and y components, so more sines and cosines. Newton's first law is also called the law of inertia, and what it says is that if there's no external force on an object, it's going to remain at rest, or it maintains a constant velocity. This is called equilibrium, either static equilibrium if the object's at rest, or dynamic equilibrium if the object is moving at constant velocity. What is inertia? We call it the law of inertia, and we talk about inertia sometimes. Inertia is the tendency of an object to resist a change in velocity. So you can imagine that a more massive object, it is hard to change its state of motion, right? We need a bigger force to make it change its motion. So in fact, mass is a measure of inertia, and the more mass you have, the more inertia you have. Newton's first law says that the net force on an if the net force on an object is 0, the object will either remain at rest or stay at constant velocity if it's moving at constant velocity. Now, when we solve problems for Newton's first law, the first thing we're always going to do anytime we solve a force problem is draw a free body diagram. Then what we're going to do is we're going to sum our forces for both the x and y axes, if there is forces on both the x and y axes, or if there's a force at an angle and a force at another angle. Any force that's not on that x or y axis, we have to split into components, but never do that on the free body diagram. And you're going to do that by using sines or cosines or tangents, whichever works for you. You're going to substitute, after you've set up your equations, then you substitute in your numerical values, and you solve for the net force in each direction. Using the net force in the x and y, then you set up a net force triangle, and you find the hypotenuse, right, Pythagorean theorem, and we get the angle, because remember, net force is a vector that has a magnitude and a direction. Let's take a look at this man. If he's hanging at rest on a rope, and he's probably saying, can you get me down from here? What is the tension in the rope if he has a mass of 100 kilograms? Well, like I said, first thing we're going to do is draw a free body diagram. So we have his weight down, right? Force of gravity. I guess I should write force. I should write force of gravity. Sometimes I write mg, which is totally fine. And we have the force of tension up. Now, he says he's at rest, so that means that my net force has to equal 0. And what are my net forces? Well, we have that force of tension up, and we have that force of gravity down, and that has to equal 0. So that means that my force of tension is going to equal the force of gravity, right? If I move that force of gravity to the other side. All right, so force of tension is equal to the force of gravity, right? The equation for the force of gravity is mass in kilograms times 9.8. So the force of tension in the rope is 980 newtons because this man's at rest, and the forces have to balance or he will accelerate. We are now going to ratchet things up a little bit. I have what's called a sine problem here. So I have a weight in this case it's a sine, it's hanging from 2 ropes, so not 1 rope anymore. And not only is it not hanging from 1 rope anymore, but it also has a rope that's at an angle. So I have this rope B that's attached to the wall. It's totally horizontal. As you can see, I drew a little axis there through the center point. And then we have rope A, which is attached at a 40-degree angle from the ceiling. So remember, the first thing we're going to do, and we're going to find both tensions. So we got 2 things we got to find here. But the first thing we always do is draw our free body diagram. So we're going to start, and we're going to use point C as our center point, right? Because all of these things attach to point C. And we have our rope TA. Sorry, this is squiggly. There is rope B. And then rope C, we're going to call that TC, but TC is really just the weight of my object, which is that 200 newtons. Sorry, I have a new pen this time, and it's a little harder to write with. So that's 200 newtons. Now, I'm going to stick this little axis back on here so we can see our rope, and we can see that tension A is not on the x or y axes, and anytime we have a vector not on an x or y axis, we're going to have to split it in components. I'm going to move this angle though. This 40-degree angle is the same as this angle down here. All right, is that like complementary angles or something? So that I can work with something that's actually on one of my axes. So there's my free body diagram. I have tension A at an angle of 40 degrees, just a little horizontal. I have tension B, which is completely horizontal. It's completely on that x-axis. And I have tension C that is vertically straight down. When I write my equations for this, because tension A is at an angle, I have to split it into x and y components. So let's go ahead and write our tension A. Let's make our tension A triangle. Never do this on your free body diagram. The College Board goes a little crazy if you do that. And they'll take points off. So never put components on a free body diagram, just always write them off to the side. And there's my angle of 40 degrees. All right, so I have my tension A split into x and y components. The next thing I'm going to do is write my force equation. Now, because it's hanging from rest, my sum of forces in each direction is going to equal 0. So my sum of forces in the x direction are going to equal 0, and my sum of forces in the y direction are going to equal 0. So let's write our x equation. What are my forces in the x direction? Well, in the positive direction, I have that component of TA, which we called TAX. And in the negative direction, I have TB. So we're going to write minus TB because it's pointing to the left. It's a negative vector. And these all add up to 0. So what that means is that my TAX must equal TB, right? They're the only 2 forces I have horizontally. Now, let's do the same thing in the y direction. So sum of the forces in the y. What do I got? Well, I have that positive component of TAY, right? It's pointing straight up, TAY here. So that's a positive vector. So we have TAY. And then down minus, I'm going to subtract, because it's pointing down, TC, and those have to equal 0. Now, there's not much I can do right now with this. I don't want to know what TAX is. I don't want to know what TAY is. I want to know what TA is. So what we're going to do now is we're going to substitute in the trig function in terms of TA. So if we look at TAX, right, TAX is adjacent. So that's the cosine of the angle, which happens to be 40 degrees, is equal to TAX over TA. Which means if we do some rearranging to solve for TAX, right, that's what we want to get rid of, we get TA cosine of 40 degrees. So I'm going to plug that in down here. Instead of TAX, I'm going to write TA times the cosine of 40 degrees, and that's equal to TB. I still can't do anything here. I don't know what TA or TB is. Sure, I could do the cosine of 40. It's still not getting me anywhere. Let's go over to the y direction. I'm going to plug in my TAY. Notice that that is the opposite. So the sine of 40 degrees is equal to TAY over TA, which means that the sine, sorry, I didn't mean to write that, that TAY is equal to, rearrange that, TA times the sine of 40 degrees. All right, so let's plug in for TA. Let's plug in our TA sine of 40. So we have TA sine of 40 degrees minus TC is equal to 100. And so that means that TA sine of 40 degrees is equal to TC. Well, what do I do? Oh, I know that TC is equal to 200 newtons. So that means that TA times the sine of 40 degrees is equal to 200. And I can just do some algebra now. That means TA, the tension in rope A, is 200 times divided by the sine of 40 degrees. So let's plug that in our calculator. 200 divided by the sine of 40 gives us 311 newtons. Yay, I know what TA is. TA is 311 newtons. Ooh, now that I know that TA is 311 newtons, I can find TB, correct? Right, if we go over to our x equation here, we can put in 311 for TA, right? That's what TA is, times the cosine of 40 degrees. That's equal to TB. So let's plug that into our calculator again. Make sure you're working in degrees and not radians. Take 311, multiply that by the cosine of 40. What'd you get? You should get 238. And this is newtons. Let's keep our units together. There's our TB. All right, so we got TA and we got TB. Two unknowns, one problem. But notice we had to do two different equations to get it. And anytime you have two unknowns, you're gonna need two equations. Cool. Well, that's all I got for you. So fill out your WSQ and I'll see you in class.